Welcome to physics. I'm excited to meet all you guys. Like I said, I read your bios. You sound like a stellar group. I'm excited to meet you over the next 13 weeks. Now, you guys just did a summer term. So you guys are already the experts. So I'll start there by saying, this is my first Zoom class. It's a little nuts. I've been teaching for like 15 or 16 years. Yeah, something like that. And one of the reasons I love teaching is I love getting to know my students, and I love my classroom. I love UVA. I went to UVA 4 times, and I love grounds. And so that's one of the reasons I signed up to be a teacher, was I get to excuse to be back on grounds and see you guys and bump into you on the corner or something, but none of that's happening. So one of the reasons I mentioned that is I got, the physics department and UVA both have been sending me like, the top 10 ways to teach online and tips for Zoom and stuff like that. This is new to me. So in any class, I always want to invite student input. This is not me just lecturing. That would be awful in person, and it's super awful on Zoom. I've been in faculty meetings where someone drones on for 75 minutes over Zoom, and it's torture. So I don't like to lecture a lot, even in person, and I think just on Zoom, that would be miserable. So my goal is to talk as little as possible. Maybe I should mention that that's, I think, a valid, and it's my favorite way to learn is not by listening to someone just talk. So if you saw my little intro video that I put on Colab, I've been studying education for a long time, and I'm pretty convinced that the best way to learn, maybe like a couple thousand years ago, was to go stand, somebody would climb up on a hill and talk and everyone would listen. That was the best source of information. There weren't encyclopedias, maybe people weren't that literate. And even a few decades ago, there were a certain number of people that were sort of the gatekeepers or the holders of knowledge in a society. And so your parents, your pastor, and your teacher, these are the people that like informed you about reality. Well, the floodgates are open. We all have YouTube. We all have the world's knowledge in our pockets. And so me talking is not usually the best way to learn anymore. There are just smarter people than me with better special effects on YouTube doing cooler stuff. So my goal is for this to become more of a dialogue, to get to know where you guys are in your understanding of physics and your understanding of the world, and like your fears in terms of physics, and just try to clear up misconceptions and engage you guys. And so, yeah, and so along that path, I always would encourage I want this to be a dialogue. I'd always encourage student participation, especially now. So I absolutely want you to stop me in mid-class or after class and say, hey, that was super boring, or we couldn't really hear you, or have you ever heard of breakout rooms? They seem cool. Or there's this other tool we used in our Orgo class that really worked, and why don't you give it a shot? So I'm here with my laptop and a webcam, and that's about it. And those are my tools right now, and lots of hand waving. And so I'm open ideas when it comes to how we're gonna do this. Okay. So my goal is to not talk, but to be kind of engaging guys in little challenges and problems. I guess the one thing we're up against is that because we're on Zoom, which I don't know. I'm not even gonna call that an impediment or like a problem. Like, I'm actually excited about the opportunities that this is gonna force people to, just new ways of learning that I think it's forcing people to engage in. So I think some people like revert to just lecturing because that's an easy way to go. So I'm gonna stand up here and talk, and then everyone else could fall asleep, but my job is just to talk. My job is to make sure you guys all love physics and crush the MCAT. That's my job. So that's what we're gonna do. At least the physics part of the MCAT. But actually, I should say, maybe that's another segue, is I think that this class will help you in the parts of the MCAT that aren't physics, and it will hopefully help you as a doctor. And here's why I say that. My hunch, and maybe people will tell me if this hunch is correct or not. My hunch is that you guys are all smart, awesome, motivated, high achieving people, and you probably got good grades in high school. And if your high school was like most high schools and college too, you probably succeeded by memorizing and repeating algorithms. That's kind of the way a lot of schools in our world work. And that's the mode of learning that we've kind of entered into, is that, okay, all right, professor, start talking. I'm going to write that down. I'm going to see if I can repeat it to you on the midterm. That style of learning is, it's great for school if you're just trying to get raise your GPA. It's not real learning. It's not lasting learning. And I don't think it helps you be like a doctor or whatever profession you're going into. And so someone that is successful in this class, I think will, something I'm going to push on you guys all semester is to, anytime you find yourself like, I'm not really sure what this equation is, but I think I'm going to plug and chug it and hopefully that'll work. Anytime you're kind of engaged in that kind of thinking where what's the equation? Give me the equation. I'm going to try to pull you out of that. And so what I want this time on Zoom to be mostly is talking about concepts and discussing the concepts and trying to clear up misconceptions and kind of drill down to what are these concepts telling us about the world. The reason I love physics is because I think arguably, maybe math is the most fundamental. Right above math is physics. It's like the most fundamental science. It's really just about what are the fundamental laws that tell us how the world works. That is a pursuit that we humans have been undergoing since there have been humans. And so I'm pretty sure the first humans to walk around went, I wonder what that is. And that is just something innate, I think, in our species. I think it's always exciting to just get to know the world a little bit better. And so that's what physics is. It's just trying to understand conceptually what makes the world tick, what are the principles and laws that undergird it, and make it knowable. And I should maybe mention, one of my favorite things about physics is that pursuit only enriches your experience in the world. And so some people think, well, if you know how rainbows work, that kind of ruins rainbows. No, rainbows are still beautiful, even if you know all about electromagnetic radiation and even stuff at the quantum level. So that's my goal for us, is to engage conceptually with all this material. And that kind of thinking will benefit you, I think, in everything else you do. So that's gonna be one of my main goals. I don't think I would want a doctor, if I walked into the doctor's office, I don't think I would want my doctor going, okay, let's follow an algorithm I memorized in med school. I'd rather have my doctor understand the systems that are at play and diagnose me and problem solve that way. Just a little more personally, my dad recently got a new doctor and basically fixed a bunch of stuff that was wrong with my dad. And this doctor, he used to be an engineer, and I used to be an engineer too, so I'm a little partial, that his thought process is about problem solving and not about algorithms. That's one thing that gets beat in your head in engineering school. My first 2 degrees from UVA were in mechanical and aerospace engineering, and so maybe that's my bias, is that I like problem solving. There's not a whole lot of memorization. Now, that said, I've been reading up on the MCAT. It's closed notes, it sounds like. It's unfortunate, this day and age, nothing should be closed notes. We all have Google. You're not gonna be like, I can't imagine a situation where you're not allowed to Google something, but it is closed notes. So you're gonna have to memorize some stuff, but at any point, anytime I introduce anything that I think you need to actually like hang on into your brain, I'm still gonna encourage you to hang on to it in a way that is tied to some network of understanding, as opposed to, okay, so what was that equation again? X equals X naught plus what again? Was that a minus? So, because under the stress of the test on test day, it's easy, if you've tried to just jam stuff in your brain, it's easy to flip a minus and a plus, or put the something on the other side of a fraction or something like that. So, but if you get it conceptually, it's just there, and it'll be there for a really long time. And so, as I've been flipping through them, I was like, oh, I mean, there's parts of physics that I haven't, everyone kind of gets into their specialty. There's parts of physics that I haven't touched in a while. And I was looking through the Kaplan review book, and I'm like, oh, I remember that. And it came back to me because I had studied it conceptually, kind of had a conceptual understanding, was able to tie it into some larger framework. Okay. So maybe I don't need to tell you guys how to learn, but when I teach physics, I usually feel like I have to get on that soapbox a little bit. Okay. I just talked for 11 minutes. That's about as much as I want to talk without bringing things up. So let's start. Does anyone have any questions? I'm gonna have to page back and forth between grids because I can't see everyone at one time unless there's like a way I haven't figured out yet. So
I have a question about, sorry.
Pardon?
Oh, I had a question about, I don't know if you were going to touch on this just now, but I had a question in regards to the textbooks for like what, I guess, where to buy them necessarily, because I think the last email I saw was that we were going to get an update on what the textbook situation was. So I just wanted to follow up with that.
Thank you for doing that. Let me see if she got back to me. I'm checking my email right now. Let's see. No. Okay, so I'm glad you asked. By the way, I'm going to refer to you guys as the names you have on your Zoom. So if you don't go by Leonardo, let me know. But so yeah, textbook situation. So I think if you watch my little intro video, I kind of didn't want to do a textbook. I think they're crazy expensive, and we have Google, and so there's just other ways to organize information other than a textbook. So I went to the bookstore just a couple days ago, and I ended up talking to a woman who works there, and she said she was going to get us just the e-version, just the electronic version of the James S. Walker physics textbook, which is great. It's a great textbook as textbooks go. So she has not gotten back to me. She said it should be by the end of this week. We should have a textbook. So that's the plan. If you want to buy yourself the paper version, great. If you want to Google it, I did find the PDF version out there on some weird website. But I'm hoping that'll be inexpensive. I think she says like $60 or no, $50, I think, for the electronic version. And it comes with some other stuff, I think. So that's the plan. And then I think WebAssign for homework is the plan. Rent it $25. There you go. Jane just put in chat. You can rent it from Amazon. How do you do that? You have to send it back?
Yeah, you mail it back in December. I did it a lot in college, and it's super easy. So
that's awesome.
Yeah.
Thank you. Yeah, I think I put a link on Colab for Amazon, and I saw the word rent, and I was like, that's weird. I never rented anything from Amazon. I'd like rent some skis or something. I don't know if you can do that, but it's just textbooks. Okay. Great question. Any other questions?
I have a question. Do we have discussion tomorrow morning?
I have not gotten an official word about that yet. I think it was going to be with a TA, but they won't get back to me about whether I even have a TA. Do you know if is there a name associated with that discussion? Like a TA or a professor?
Just says 2010 when I looked last.
Yeah, discussion section. What time? I'm gonna write that down.
11, I think.
Yeah, 11. It looks like 11 to 11:45, maybe.
Okay. They haven't gotten back to me about that, but I'll
It says 11 to 11:50 with you, Dr. Shields.
Really?
Yeah.
All right. Check my calendar. That sounds great. Let's do it. Let me see. Tomorrow's Wednesday.
Mm-hmm.
I can probably do that. Let's click. So if you can't tell, not all the gears are meshing right now. So I want to be honest about that. This semester is going to be awesome. We're going to learn a ton of physics, the mechanics of when discussion is, when the textbook's going to come in, that's gonna maybe be a few days till I get hammered out. And which means we can't do homework tonight because WebAssign isn't up. But I think I do have one homework problem I'm gonna ask you to do. But sure, let's do discussion. So my sort of yeah, I'll put something on Colab. Let's do that. Cool. Good. Okay. Should we do some physics? All right. Now, I don't know what y'all's physics experience is. By the way, if you like took physics before and it didn't work, I'm really excited that we're gonna flip that. And you're gonna love physics. This is gonna be great. Okay. So I don't know where we are. We're gonna give this a shot. I want everyone, every class, I think you should have pen and paper on you. So if you don't have pen and paper, quick, grab a pen and paper. Looks like everyone's ready. Nope, Alex had to get up. Claire's getting something to write on. All right, pen and paper in hand. I would like you to draw a plot. Remember those, right? Two orthogonal axes. I would like you to draw a plot. I would like you to draw the velocity versus time plot. Velocity versus time. The convention is when you say velocity versus time, velocity is in the vertical axis, time's in the horizontal axis, right? Draw the velocity versus time plot of something dropped, entering free fall, then reaching terminal velocity. So you're gonna plot the velocity of an object that got dropped and eventually reached terminal velocity. Now we're gonna try a zoom trick. I'm gonna click a button right now, and I think you're all gonna go into rooms. I've not done breakout rooms yet. Have you guys done breakout rooms?
Yeah.
Yes? Wait, it works?
Yeah, it works.
All right. You could, and I'm open to critique. So if after this you're like, don't do that again, let me know. I'm about to send you into 7 different rooms. That'll be about 5 people per room. I want you to share your answer with everyone in your room, and I want you to discuss for like 2 minutes. Okay? And then I think after I click it, hopefully I'll be able to figure out how to get you all back. So I'm gonna send you into 7 different rooms, automatically assigned, and I want you to just talk, say what you did. You can put up on the screen, say, oh, this is what I did. I think it did this, and I think it did this. And hopefully there'll be some disagreement and you can discuss, and then we're gonna come back. Cool? Mm-hmm. All right. I'm clicking the create rooms button. We'll see what happens. Oh, that's awesome. It did it. So we're all open all rooms. All participants. Oh, you get invited, I guess. Okay. So you have to say, yeah, cool. Bad at Zoom. Okay. Thank you. I sent everyone a message that said, you got 30 more seconds. Then I hit close after 30 seconds. And then Zoom said, nope, we're going to give everyone 60 more seconds. So I just learned something about breakout rooms. But everyone's coming back. Let's see. I think we're all back. Sweet. Okay. That went as good as it could have gone, I think. So I'm happy to cold call on people. Would anyone like to share whether their room came up to a consensus, and if so, what the consensus was?
Yeah, so our room, so I can't hold up my screen because I'm writing on my tablet, so like it just whites out, but we basically came to the conclusion that the graph would be increasing from left to right, and then as it got to terminal velocity, it would basically plateau until it kind of remains constant when it reached terminal velocity.
Remains constant. So it's gonna increase, but gradually plateau.
Yeah.
I like it. That sounds good. Anyone else? So what? Let's see. Just kind of gradual, or is it gonna like hit it and kind of take a sharp turn, or just gradually plateau? What do we think? One other group. Just tell me whether another group, yep, that's what we got, or no, we thought it was going to increase forever.
We had the same answer, and we felt like it was going to gradually reach terminal velocity.
Gradual. Okay, thank you, Alex.
We
Cool.
also have the same, yeah.
And that was, I missed it.
It was Rachel.
Oh, hi, Rachel. Thanks. All right, we're off to a good start. You guys get some physics. So let's take a look at that plot, and then I want to talk about some of the physics that is under why that is the case. That's what I got right there. Yep. So I have my velocity. So by the way, velocity versus time plot, one of my favorite plots. And we're going to talk about why. So this is velocity versus time. Velocity is the value being plotted here. And as time goes on, the velocity in this case is changing. In a second, we'll talk about why it's changing, but let's just for now say it's changing. The reason this is my favorite plot, there's a bunch of stuff going on in here. For starters, the velocity is plotted. So it starts increasing. Notice it starts increasing. Is this working if I just point my finger like that? Okay. There's lots of ways I can, yeah, this is crazy. So it starts increasing, but then notice the rate at which it's increasing is decreasing. So it's increasing, but at a decreasing rate. So it starts kind of steep, and it gets less steep, less steep, less steep, and then it reaches an asymptote or a plateau, meaning it's not increasing anymore. And it reaches its terminal velocity. So the reason we call it terminal velocity because it's not speeding up anymore. Let's talk a little bit more about the plot, and we'll talk about the physics. So the plot, what I love about the plot, it's telling me about velocity. I can visually see the velocity, which, by the way, I know this works in physics. I bet this works in most classes, most subjects. My brain engages if I can draw myself a picture, especially in physics. So in physics, we're going to be talking about physical things. So for part of the semester, we'll be talking about, you know, whatever, I don't know what we were dropping here, cannonball. So we can, physical objects, cannonballs, pizzas, cars, whatever. And then even when we get into more abstract stuff, you can still draw it. And so this is physics, it's the real physical world. And so anytime I can kind of draw what's going on, whether it's a picture, I might just draw the bowling ball. Your brain's going to engage a little bit, especially I think plots. It's a good way to think through what's happening. So as I draw that, I see my velocities increasing. By the way, if you drew your plot like this, you agreed with my arbitrary choice of down as up, right? Drop something, it's going to go down. If you drew your plot like this, you labeled the downward velocity in the upward direction. That's arbitrary. Coordinate systems are arbitrary. So if you drew it like the mirror image of this, that would be down is down, and that's also fine. So I can see what's going on in here. I can see that it's increasing at, then that starts to taper off, and then eventually reaches this thing. I might even label my asymptote as d sub t or something, terminal velocity. Also on this plot, I'm seeing the rate of change. Now, the reason I want to bring that up is that phrase I just said is one of the more important phrases in physics, and again, I bet other subjects. So if the subject you're studying, chemistry, biology, physics, isn't static, if it has change, we're usually concerned with the rate of change. And the rate of change is just amount of change per some other change. And we should be pretty familiar with that. The per whatever, the thing that's on the bottom, the per whatever, it's usually a unit of time, but not always. So when I say my car is going 60 miles per hour, that's a rate of change. My car is changing its position 60 miles every hour. So it's an amount of change, position, per what? Per hour, some unit of time. So I might say there are 5 people walking down the corner every second. Or there are, I don't know, there's some other rate of change. the plumbing in my house handles 5 gallons per minute. There are 5 coulombs per second traveling through my USB cable. So it's a rate of change, and it's usually per time, but not always. So I might say that like my happiness level goes up, or my alertness level goes up by 3 alertness units per cup of coffee. And so not necessarily a rate, a unit of time. My happiness level goes up 3 units per donut. And so it's just some rate of change. So 1 donut will create this much change in my happiness. And the rate of change might not be constant. If you're eating donuts, your rate of change probably does this, and then eventually you get so many donuts, it starts to maybe even go down. Starting to get sick. So hugely important concept, rate of change. So on a plot, the rate of change is represented by the slope or the steepness. And so in this case, my velocity is changing, and the rate that it's changing is the steepness, which we call acceleration, right? So let's talk units for a second. And then in a couple minutes, I will have talked enough that we'll have to take another break. Let's talk units for a second. America is one of 3 nations that still uses all that crazy stuff like pounds and furlongs and twips and barleycorns. Us, Liberia, and Myanmar, I think, are the 3 nations. Everyone else has figured out it's so much easier to just chop everything up by thousands. That's just way, way easier. If I keep teaching physics, I'm gonna move to another country because it's just crazy that we do that. In this class, I hope the MCAT, I hope we can get away with just using those units. So in this class, we're gonna primarily use MKS units, meters, kilograms, seconds. So let's talk about meters is our measure of displacement. So most of what we talk about this semester, and again, this probably applies to other classes, we're gonna chop up space into a Cartesian coordinate system. Thank you, Descartes, for coming up with that system where we just pick an origin, that's arbitrary, pick an up and a left. On Zoom, I don't know if, is that left? Yeah, okay. Or pick it up and a right, let's pick it up and a right. Pick it up and down and a left, right, whatever. So pick an origin, that's arbitrary. Pick an up, that's arbitrary. Pick a right, that's arbitrary. But the left, those 2 should usually be orthogonal, right angles to each other. Ortho means right, orthodox. And go from there. Now, like I said, that's arbitrary. If I'm doing a problem and everything's falling, why not flip my coordinate system upside down and just have down be positive? So one thing that sometimes people tend to want to memorize is, oh yeah, down's negative, right's positive. I don't know. That is not something to memorize. That is completely arbitrary. When you're working on a problem, pick a coordinate system and stick with it, and you're going to be fine. For some problems, if you're doing like something going down a ramp, you might want your coordinate system to be parallel and orthogonal to the ramp because that object is moving in that axis. So coordinate system is arbitrary, but we chop up space into X, Y, Z, and we usually measure your place in that coordinate system in meters. Physics, we use meters. So I'm at the origin, I'm at 0. I walk a meter that way, my displacement is 1 meter. If I am the rate at which I'm displacing myself is my velocity. It's the rate of change of position. And so if meters is my measure of position, the units of velocity are going to be meters per second. That's not something to memorize. That's literally just that's the definition of a rate, is a something per something. And if it's per time or per second, it's meters per second or whatever per second. How quickly my position is changing. One of the reasons I wanted to bring up units right now, and we're going to pay attention to them all semester, is that when you're trying to understand a problem, often the units are like a guidepost to some degree. So for example, if I want to know, if I told you I was going 20 miles an hour and I went for 3 hours, tell me how far I went. Hopefully just conceptually you're like 60 miles. That's not hard, right? You're going 20 miles an hour for 3 hours. But if you were writing it down and you wanted to check yourself, 20 miles per hour, miles on top, hours on the bottom, times 3 hours. The hours are going to cancel out, and I'm going to end up with miles. So like a lot of times the units help us understand what's going on. Later in the semester, we'll talk about electric field. Electric field is measured in newtons per coulomb. That seems crazy, but it helps you remember that, oh, that's what a field does. It pushes. A newton is a measure of push on coulombs. Coulomb is a measure of charge. Electric field can also be measured in volts per meter, also very descriptive. If I'm in an electric field that has a certain number of volts per meter, that just tells me if I go 1 meter, I'm going to go through that many volts. And so I think paying attention to the units is very helpful. Okay, so on my sheet, I'm going to write next to my velocity, I'm going to write meters per second, and I'm going to write seconds on my horizontal axis. So I wrote seconds on the horizontal, meters per second up here. If I were to measure the slope at any point of my plot, I might calculate that slope. You remember slope from like algebra class, geometry class? It's rise over run, right? Remember rise over run? Hopefully everyone's heard that term. Yeah, okay. So if I were to measure, in this case, rise is measured in meters per second, over run, which is measured in seconds, the units will be meters per second per second. That's what we call acceleration. It's just how quickly you're changing your meters per second, or how quickly you're changing your velocity. So acceleration is just the rate of change of velocity. Velocity is the rate of change of position. And so if I'm changing my meters per second, the units of that are going to be meters per second, or meters per second squared. So if my car goes 0 to 60 in an hour, the rate of acceleration is 0 to 60. That's the change in velocity per hour. That'd be 60 miles per hour squared would be my rate of acceleration, how quickly I'm changing my acceleration. Okay, so acceleration or rate of change of velocity is on this plot. Last thing before we take another little challenge. My acceleration's on here, so is my displacement. And again, I can see that if I think about my units. My displacement is actually the area under there. So my displacement is the area. If I have this property, this thing called velocity, you can think of that as a property where I am accumulating changes in position. I'm changing my position. So I started at x equals 0, and my velocity is 10 meters per second. After 1 second, I will have gained 10 meters of displacement. I will displace myself 10 meters. I'm going 10 meters per second. So after 2 seconds, I've got another 10 meters of displacement. Now I'm 20 meters from where I started. And I will accumulate that displacement while I have a positive velocity. If I start going with a negative velocity, that simply means a negative rate of change. It means I'm giving up some of that displacement. So I'm going in the other direction. So negative rate of change is definitely possible. I can be losing displacement every second. If I'm giving up 10 meters per second, I'm going from 20 to 10 to 0 to negative 10 to negative 20. And so that is also seen here. How fast I'm going determines how quickly I'm gaining displacement. So down here, when I wasn't going very fast, I wasn't gaining displacement. I wasn't gaining area under the curve very quickly. Once I was at terminal velocity, every second I got a big rectangle of displacement. But down here at the beginning, I wasn't going very fast. My displacement wasn't changing very quickly. So I can see on this one velocity plot, I can see my acceleration, I can see my velocity, and I can see my position. Position, rate of change of position, and rate of change of that. Pretty cool. One last note, on this plot, you can see that right at t equals 0, right when I let go of this object, it was accelerating the most. It had the steepest curve. That acceleration on Earth is the acceleration due to gravity on Earth. And in MKS units, it's 9.8 meters per second squared. I'm not going to ask you to memorize that. I'm just hoping it eventually sticks in, but it's a good thing to know, 9.8. Or on a problem that you only have a few seconds to work on, just use 10. But that's the steepest. So the slope of the line right here is 10 or 9.8. That's the slope of that line. And that slope starts diminishing as, anyone have a guess? Like, why doesn't it just go like straight line forever?
Air resistance.
Precisely, Jay. Jay hasn't been in school in a while, but he still got it. It's air resistance. So when I first, air resistance is a velocity dependent force. Don't know if you need to know that, doubt you need to know that phrase, but it's just a force that changes over time. So there's even a rate of change of that. And so when I let go of the object, it's not going anywhere. There's no air resistance. As it speeds up, the air resistance increases, and eventually, when you're going fast enough, your weight down is canceled out entirely by the upward force of air resistance, and you don't accelerate anymore because there's no net force on you. Pretty cool. That air resistance is velocity dependent, and it's also surface area dependent. Fun fact, that's why chalk dust floats, because there's hardly, it's very light, but it's got a lot of surface area per weight, and so it reaches terminal velocity almost immediately. So if you take a piece of chalk from a chalkboard and drop it, you'd have to drop it off a 50-story building in order to reach terminal velocity. Chalk dust reaches terminal velocity almost instantly. Its weight and its air resistance almost immediately cancel out. And so you can, one little current of air, you can actually get the upward force of air resistance to exceed the weight of chalk dust, and it starts moving up. So that's why it flows around in these air currents. Try that sometime. Okay. I think that was it for that. Any questions?
What did the 9.8 stand for or represent again?
Excellent question. Thank you. I threw a number out there. I told myself I was going to use any numbers so early, but I threw one out there. That is the acceleration due to gravity near the surface of the Earth. So if I were to drop, great question. If I were to drop something right now, it would accelerate, meaning change its velocity. And it would do that near Earth at 9.8 meters per second. That's a speed, that's a velocity, per second. Meaning, if I drop something off a cliff, 1 second later, it will be traveling 9.8 meters per second. Because it's meters per second squared, that's meters per second per second. 2 seconds later, or 1 second later, after 2 seconds of free fall, it'll be traveling 19.6 meters per second. And 1 second later, it'll be going, what, 29.4 meters per second. So it's going to keep speeding up at a constant rate without air resistance. So if I were to drop something off a cliff and I was neglecting air resistance, its velocity plot would look like that. And that slope is 9.8. It'll be going 9.8 the whole time. It'll be accelerating at 9.8 the whole time, speeding up at 9.8 meters per second per second. So after 1 second, it'll be going 9.8. After 2 seconds, it'll be 19.6. Like that. I don't know if you can see that. Does that make sense?
Yes.
Okay. So far what we've been talking about is position, rate of change of position, and rate of change of that. Position, velocity, and acceleration. Cool. Should we do another activity? I don't know if I'm gonna, I'm gonna not send you into breakout rooms for this one, because I don't know how. I'm gonna share, let's see, hold on a second. Let's try this. So if I shared this, so if I share that, everybody can see that?
Yeah.
Yeah.
If I send you into a breakout room, if I'm not in the room, you probably can't see that. In fact, while I'm screen sharing, well, there's no way that would work, right? I can't send you in a breakout room.
Yeah, I think
You
what
can take a
some
screenshot
professors-
too.
Yeah, we could screenshot.
Let's just do this. Do you want to try that? Do you want to try screen? Or we can just stay out here and everyone can just work on it for a couple minutes.
Okay.
Let's just do that. So here's your challenge for the day. I think we'll do, yeah. Okay, so this, I just talked all about velocity plots. You're now looking at a position plot. So, yeah, maybe I shouldn't have done that because you're now looking at a position plot. So you're now looking at a position plot. Actually, I'm gonna talk to this slide for a second, then I'm gonna let you go. So what I wanted to get across in this little set of questions is the idea, the distinction between instantaneous and average velocity. And then I'll let you go. So that's important. So a second ago I said, Washington DC is about 100 miles from here. If I told you it took me 2 hours to get to DC, all you could conclude was that I averaged 50 miles an hour, because that's all the information you have. You know my change of position, and you know how long it took. So you know I went 100 miles in 2 hours. So if I told you I went 100 miles in 2 hours, you could conclude I averaged 50 miles an hour. Does that make sense? So I went 100 in 2 hours. My average velocity was 100 divided by 2. But you don't have any information about, so that's all you can say is my average. But you don't have any information about my actual velocity at any moment, my instantaneous velocity. So what I might have done, I might have traveled at 30 miles an hour for an hour and then gone like 200 miles an hour the rest of the way. Or I might have traveled 60 miles an hour and taken a break. So there's a lot of other ways that could have happened. But if the only information you have is that I went 100 miles an hour in 2 hours, you can tell me my average. So at the top of this slide, I'm asking you to just tell me my average velocity in certain delta t's, in certain changes in time. So for example, A, in the first 2 seconds, my average velocity was how far I went. It's like 10 divided by how long it took me. That's my average velocity. But down at the bottom, I'm asking you to just tell me my instantaneous velocity, which is how fast am I going at that moment, at that second. So you look at the top, it's always ranges. It's 0 to 2 or 0 to 4. The bottom, it's always just what's my velocity at 1? What's my velocity at 3? And my velocity there is just the slope, the rate of change. Any questions about that before I give you like 4 minutes on that one? Okay. Let's just work on that for 4 minutes. I won't try the breakout room thing. Feel free to like think out loud if you want to while you're working on it. It's fine, but I'll check back in like 4 minutes. Okay, so that was a little bit of practice. Hopefully that went well. If it was confusing, today is just our first day. Definitely don't be stressed that didn't make sense to you. We're gonna talk about it. So like I said, I want most of our time in these 75 minutes to be just talking about the underlying concept. So I've got a plot up there. I love plots. This one's position versus time. And on that position versus time plot, I can see the rate of change, and that's the steepness and or the slope, and that's what we're asking for at the bottom. At the top, I'm looking to calculate the average velocity, which is my displacement divided by my time. So for A, B, C, D, and E, I just have to figure out how far I went and then divide by the amount of time. What did we get? Someone unmute themselves and tell us what we got for number 1.
Two and a half.
For A, let's take a look at A. We went 10 meters in 2 seconds. So the average velocity in that case was how far I went, 10 meters divided by 2, so 5 meters per second was my average. Which, by the way, in this case, that's actually the slope of that line the whole time. The whole time I was going 5. The slope of that line is 5. You can see after 1 second, it crosses right between 4 and 6. So I've gone 5 meters in my first second, and 5 meters in that second. So for A, I was going 5 the whole time. For B, from 0 to 4, I wasn't going 5 the whole time. So from 0 to 4 seconds, I'm going 5 meters per second for 2 seconds. Then I'm going negative something, and then I'm even going flat. Well, that's at 5 seconds. So I'm going positive and then negative. I have a negative rate of change from 2 to 4 seconds. But if I just want to know the overall average velocity from 0 to 4 seconds, I just got to see how far I went. Looks like I went 5 meters of total displacement. So by the way, I went all the way to 10 and came back down to 5. So I traveled 15 meters. So if you wanted to know your average speed, we don't need to get into that right now. It could be 15 over 4, but that's not what I want to know. I want to know how far did I go, and my total displacement over the first 4 seconds was 5 meters. I started at 0 and I ended at 5. I went 5 meters, and it took me 4 seconds. So 5 over 4, 1.2 meters per second. Displacement over time. How we doing? Cool. C, from 2 to 4 seconds, I was at 10. At 10, I was at 2 seconds, I was at 10. And later, I was at 5. What is my change if I go from 10 to 5?
-5.
Negative 5. So I lost displacement. I went from 5. I went from 10 to 5. That's a change of -5 over 2 seconds. So my average velocity was negative 2.5 meters per second, which is the slope of that line for that whole duration from 2 to 4. From 2 to 4, that's a slope of -2.5. From 4 to 7, I go what? From 5 all the way down to -5.
-10.
So -10, yeah. I lost 10 meters, -10 over 3 seconds. So -3 1/3 meters per second. And how far, for E, how far did I go over the whole duration, over the whole 8 seconds?
Was it 0?
0, correct.
Or-
So if you've ever run track, start at the starting line, run a 400-meter dash, you didn't get anywhere, you're back at 0. So your average velocity, even if you're Usain Bolt, your average velocity when you run a 400-meter dash is 0 meters per second. You did not displace yourself over that period of time. You started at the starting line, you ended at the starting line. You had no displacement over those over that time.
Dr. Shields,
Yes, sir.
you had talked about displacement as being the amount of area you've covered, maybe in one example, and relating that to the area under the curve. Is that correct?
Yeah, so great question, Alex. Displacement is how far I've gone from where I started, and that is represented as the area under a curve. Let's see.
Because like in the first two examples, like A from 0 to 2 seconds and then B 0 to 4, it seems like that's more
Yes.
area, but your position has actually gone.
Exactly.
Yeah.
So that's why I screwed up by using this example, because we were talking about velocity versus time plots.
Okay.
The area under this curve is meter seconds,
Okay.
which is not really a sensical term. So how many meter seconds did you go in these 8 seconds? Looks like a positive number, but yeah. So if we had more time, we could maybe draw the velocity plot of this. So it's like positive velocity, positive velocity, negative velocity, 0 velocity, negative velocity, positive velocity. If we were to draw that plot, might be fun to do for homework, the areas would cancel out because you didn't get anywhere. You had some positive displacement and you had some negative displacement. Great question.
Great.
And that's totally my bad for talking about velocity plots and then switching it up on you. Okay. And let's just talk about the instantaneous real quick, and then we're done with sample problems. The instantaneous velocity is how fast you're going at a moment, not over a period of time. And in this case, how fast am I going at t = 1? I just need to find the slope at those point. So the slope at t equals 1, we already talked about, it was 5, right? That's the slope of that line all the way from 0 to 2, and that includes 1. At 3 seconds, we already figured that one out. From 2 to 4 seconds, and that includes 3, I was going, what, negative 2.5, I think it was. Yeah. So 5, negative 2.5. What is my velocity at 4.5 seconds? Someone unmute and tell me what the velocity is.
0.
0. The slope of that line is 0. That is a 0 slope. I am not going anywhere. That's my velocity. The slope of my position plot is my velocity, and that's 0 at that point. And then finally, it's 7.5. What is that? 5? Looks like 5. So it looks like I'm going 5. The velocity at 7.5 is a positive, and I got to do rise over run to figure it out. And it looks like my rise is 5 over that last second. Looks like I went from -5 up to 0 in that last second.
Dr. Shields,
Yes, sir.
are we going to be using derivatives, integrals, or any like calculus math in this, or more algebraic approaches?
As much as it kills me to say this, no calculus. So,
Wow.
Great question. You might, if you've taken calc, I mean, this is calculus. That's all this is. So rates of change. That Newton invented calculus because he was doing all this math that involved change, and so he said, I need to invent some new math. He invented calculus, and calculus is the math of change. But we're going to be fine because we're going to be dealing with changing quantities, but they'll be constantly changing, so algebra can handle that.
Okay.
Yeah, algebra will really handle that. Let me know if you, at one point you want to throw some calculus, and then we can do that. Yeah. Any other questions? I'm going to stop sharing, I think. Okay. Oh, by the way, just got an email, literally, from Jane at the bookstore. Just heard back, let's see. Oh, she sent me too. Great news, the Walker book has been approved. I will send that information to your LMS coordinator, that's Colab. So I think it'll just like show up in Colab or something. So that should be soon. That'll be great. And then she just heard back from WebAssign for your homework assignments. I'm copying her. So this is all happening like real time right now. So I wish I had this all tidied up and ready to go for the first day of class, but give us a couple days. I think we'll be in good shape. I wanted to have a couple minutes at the end for any other questions before I do a little wrap up. Is there any other questions about how class is going to run, about what the heck acceleration is, about that last problem, anything?
Yeah, I had one question about the average velocity. So we said that if for E, the 0 to 8 second like, velocity would be 0. Is that the case for every single sort of like graphed velocity that we're going to see, or is that only because that specific velocity is happening at like a repeating interval or something? Because like, yeah.
I think to answer, I'm going to try to answer that question. Feel free to re-ask it. That what I was trying to get across there is first two things. One, that the difference between instantaneous velocity and average velocity. Instantaneous is just how fast you're going at a particular moment. Average is over some delta t, a couple seconds, 2 hours, whatever. And when you're calculating, in either case, it's a slope. In either case, it's the rate of change or a slope. And the way we're going to calculate slope in this class is rise over run. So in any case, whether it's instantaneous or average, I need to know what is the rise over run. In other words, what's my change in position divided by my change in time. And by the way, that also goes for any other changing quantity we'll talk about. So I could have asked, we could have been looking at a velocity plot, and I could have asked, what's the average acceleration? The average acceleration would be the change in velocity over change in time. And so next class, I'll probably use some actual equations. I try to avoid seeing equations before I understand conceptually what's going on. Because sometimes, like I said, the tendency is just, oh, there's the equation, I'm gonna plug and chug. But so conceptually what's going on is I need to know what is the change and what is the, how long did that take? And that's my rate. So if I can calculate velocity by knowing my change in position over change in time. And I can calculate acceleration by knowing my change in velocity over change in time. So that's where we're going to start the semester. Oh, by the way, there is so much material to cover for the MCAT. So we're going to move at a pretty quick rate. We're starting with kinematics. It's a pretty good way to start. And like as a quick recap, one of the reasons I like to start there is all the physics we're going to learn this semester. Maybe a little bit at the end won't be classical mechanics, but just about all the physics we're going to learn is classical mechanics. And these are understandings of the world and laws of motion that came about in the late 1600s with guys like Newton. And so that's where we're going to start. And so if we're going to discuss the world, if we're going to talk about the physical universe, that's usually a pretty good place to start, is discussing space and how do we chop up space? How do we describe things spatially? And so right now you and I are sitting in a chair, and if that chair is the origin, I can then describe my Saturn V as like -4 meters that way. Yeah. And that's -4 because I called back negative, but that's arbitrary. That could be the positive direction. That could be the positive direction. I don't know. So we want to be able to describe the world. We want to describe the world mathematically, where things are in the world, how quickly they're changing, and how quickly they're changing. That is important to be able to do. So we've got position, rate of change of position, velocity, rate of change of velocity is acceleration, and the units are meters, then meters per second, then meters per second per second. Fun fact you might have ever seen, there's a rate, you can change your acceleration. Rate of change of acceleration is jerk. And if you're a roller coaster designer, you're concerned with jerk. So jerk is meters per second cubed, how quickly you're changing your acceleration. Even elevator designers, I think, are concerned about that. People get sick when there's a lot of jerk. And rate of change of that and that and that is snap, crackle, and pop. So you can have rate of change of rate of change of rate of change of rate of change. So I think the units for pop is like meters per second to the 6th or something. So that's where we're going to start. And then we didn't get to it today, but next class we'll talk about why stuff changes, and the answer to that, we'll preview, is forces. So we're going to start talking about forces. Cool.
Dr. Shields,
Yes.
on Colab, you have a section for iClicker, and for remote iClicker, do we need to garner one? Or are we going to use like the iClicker app or not at all?
That's for attendance, right?
There's some like
no, it's
in-class quiz things you can use it for.
Yeah, polling and stuff. I inherited that Colab site. I think, again, if people love iClickers, we can do it. I think you have to pay for it, right?
We all have access to it already for another class.
You do?
To the web module where we just log in at the beginning and answer polling questions.
If I think that will be pedagogically advantageous, then yeah, I'll come up with a reason to do iClickers. If you've already got access to them, sure. But no, I used iClickers in a class I was teaching. There were 250 people in the class, so that was how I took attendance, was I asked a polling question and everyone clicked in. But I feel like today I've been able to say, so everyone get that? And I just get a lot of this or a lot of this or this or. So that'll be our iClicker, I think. It's just head gestures.
Thank you.
Okay.
Thank you.
Good question. I'm paging between my screens here, see how everyone's doing. I don't want to wrap up early. We got 5 minutes.
I have a question.
Yes.
So are we just going to use this link then tomorrow at 11? Are we doing that? And also do we have homework due Thursday on WebAssign, or
Yeah, so I got to move that. Looks like they got us WebAssign as in like 6 minutes ago, but I'm going to have to push that homework back a day because probably be another day before I get it all figured out. So I'll change the syllabus to reflect that. So the homework will be pushed back a day. And then I think what I'll do for office hours is, actually, again, here's something I've been trying to figure out, and polling 35 people might be a good way to figure this out. When I go into my Zoom app, I can schedule a meeting and then it comes up with a crazy URL with like some bunch of stuff. But I also just have my own Zoom URL. It's like virginia.zoom.com/shields. And I could just use that for everything. I can't think of a reason. Oh, wait, it's the recording maybe. Yeah, I'll probably schedule office hours. Or how about this? I don't think we need to record office hours. So office hours will just be my link, my whatever link. And I'll send that out. It's, like zoom.com/Dr. Shields, I think. Cool. But I'll send that out on Colab. What's the best way? Should I use the email list? Is that a good way to get in touch with everyone on?
Yeah.
Okay. So I'll send stuff on the email. This is a wacky world. I'm sitting in my house teaching at UVA, and so I got to figure out email and Zoom and everything. But you guys are amazingly helpful. Thank you. I'm feeling better about the class right now. I don't know about you.
So our homework is tentatively due Friday.
Yes, actually, I'm glad you brought it up. So your actual homework that will count for a grade will be due Friday. Here's your homework that I won't grade, but I thought it would be fun. Okay, let's see. I'm going to share my screen. And this you will have to take a screen capture of. There. Can everyone see that?
Yeah, I see it.
Okay, great. Thank you. So that's your actual homework. I'm not going to grade it. I've got Isaac driving at a constant speed. So if you were to graph his velocity, it'd be straight. He's going to pass Albert at t equals 0. At t equals 0, Albert's velocity is going to do this with a steepness of 6, with a slope of 6. At some point, where is it? How long is it? 3. So I want you to write down, see if you can write a function, Isaac's position x equals what? And then Albert's position x equals what? See if you can write a position as a function of time. See if you can do it, not being graded. See if you can figure out how long it takes till Isaac is caught, meaning their positions are the same. And see if you can draw both their plots. And in fact, maybe I should have put 4 up at 1, because like I said earlier, I think drawing plots should help engage your brain a little bit. So maybe before you even start, see if you can draw. I already described that Isaac's plot, his velocity plot is doing this. Albert's velocity plot is a constant slope. So there's the 2 velocity plots. And then what's the biggest lead or the biggest gap Isaac gets on Albert? So this is just a fun challenge to do with position velocity acceleration, not for a grade, but bragging rights for whoever comes back next class with a beautiful plot they can show us. Okay.
So will we review that tomorrow during the discussion or Thursday during class?
How about tomorrow during discussion? If you have any questions about it, we'll clarify, but I don't want it. We'll start next class probably by getting into this problem.
Okay.
So discussion will just be if you have any other general questions about stuff. Cool.
So is tomorrow's discussion optional, or should we just come?
Tomorrow's discussion will be optional. Yeah. So yeah, tomorrow's discussion will be just if you've got any questions. If today was just like, oh my God, you're killing me, I need you to clarify some stuff or whatever. So pop in tomorrow for 5 minutes if you want to just come in and say, hey, you spelled something wrong on Colab or whatever. Just pop in for a minute. Totally optional. And then we'll talk about Isaac and Albert in their little car race on Thursday. Cool.
So just one quick question, just to make sure. So just to make sure I'm not confused. So the homework is pushed back like a single day, not like a class period day. So it is due on.
Oh no,
Friday.
it'll be a whole class period, and then
Okay,
it'll
so-
all be clear on the syllabus. Yeah, somebody said Friday. I meant one whole class period.
Okay.
Great question.
Professor Shields, so
Mhm.
you said tomorrow was optional. Does that mean going forward, all Wednesday discussion sections will just be for questions and optional, or?
Let's just say tomorrow's optional, and then I'm gonna see if I can make the rest of them. We'll see. We'll figure out what the rest of them are gonna mean later. So tomorrow's optional. We'll figure that out. Good question. Okay. Physics. This is great. You guys are awesome. I'm excited to see a bunch of you tomorrow, and then we'll get going again on Thursday.
Thank you.
Thank you so much.
Thanks.
Thanks.
Thank you.
Have a great night.
Thank you.
Thank you.
And
Thank you.
Professor, will you post all the recordings on Colab, or are you just recording it for?
Yeah, why not? If that's
Okay.
helpful.
Helpful.
Yes.
Especially with Wi-Fi issues, sometimes it cuts out for some of us.
Oh, good point.
Yeah.
Yeah, I'll probably post it. I don't know how long it's going to take for Zoom to process this recording, but as soon as I get an email that says that's been done, I'll stick it on Colab,
Thank you.
and I'll figure out where on Colab to do that. I don't know if there's like just links. I probably, I'll stick it in the syllabus. I'll just stick a link on the syllabus. Yeah. So after I'll add a column on the syllabus.
Thank you.
Cool. All right, my pleasure.
Thank you.
Thanks, Dr. Shields.
Thanks. See you Thursday or maybe tomorrow.